Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is the third series of problems which I presented, and these problems covered the early topics in fluid mechanics and hydraulics on properties of fluids, gas laws, and pressure at a point. Problem 13. A shaft 150 mm in diameter is inserted concentrically into a sleeve that is 1 mm in diameter greater than that of the shaft. The gap between them is coated with oil with a viscosity of 0.08 Pascal second. The sleeve is 400 mm long. So what force in newtons is required to push the shaft in order to move it at a uniform rate of 0.6 meter per second? So for the solution, let's have the figures as our guide in analyzing this problem. So we have here the shaft, and this is the sleeve 400 mm long, and at the end view we have the pushing force which causes it to move at a constant uniform rate of 0.6 meter per second. And this is the end view. The diameter of the shaft is 150 mm, and that of the sleeve is 151 mm. Therefore, the gap between them is 1 mm divided by 2, which is treated as y. So the force is equal to viscosity times shear area, or the area parallel to the force, which is equal to the circumference of the shaft times the length, or pi dl, where d is the diameter of the shaft and L is 400 mm or 0.4 meter, times U divided by Y. So viscosity area U over Y. So viscosity is 0.08 Pascal second, the area is pi dl, and U is given divided by Y, which is 1.2 over, 1 over 2, 0.5 mm or 0.0005 meter. So everything is there, then we just substitute. So y is 1 mm over 2 or 0.5 mm or 0.0005 meter. Then area is pi dl, pi times 0.15 meter times 0.4 meter, or the lateral area of a right circular cylinder, the contact area. So 0.06 pi meter square, substitute. F equals 0.08 times 0.06 pi times 0.6 over 0.0005. So the force is 18.10 newtons. Problem 14. A container in the form of an inverted right circular cone is 900 mm across the top and 1.2 meters high. It contains oil of specific gravity 0.86 at a depth of 750 mm. Determine the mass and weight of oil in the container. So for the solution, here is the given figure, and the depth of oil in the conical container is 750 mm. The depth of, or the height of the container, which is 1.2 meters. Then the diameter at the top is 900 mm, so the radius is 0.45 meter for 50 mm. Then the volume is unknown, specific gravity of oil 0.86. So this volume is similar to the parent volume. So we can use similar solids approach here, although you can apply similar triangles to solve for the radius. Then you can compute the volume of this conical portion, but the easier way and direct way is the similar solids, because this is similar to the parent container. So the density is 0.86 times 1000, so 860 kilogram per cubic meter. Mass is density times volume, and the volume can be found by similar solids. Then weight is mass times G, or specific weight times volume, where the specific weight is 0.86 times specific weight of water. So volume over height cube equals volume of container or cone as to height of container or cone cube. The volume of cone is pi r square h over 3, or in general area of the base times height divided by 3. So it is pi times 0.45 meter quantity square times 1.2 over 3. So the volume of the container or the cone is 0.081 pi cubic meter. So substitute here, volume as to 0.75 cube equals 0.081 pi as to 1.2 cube. So from there we can solve for the volume of the oil, 81 pi over 4096. Substitute here, mass is density 860 kilogram per cubic meter times 81 pi over 4096 cubic meter. So the mass can now be computed in kilograms, 53.43 kilograms. Then for the weight, we just multiply this by 9.81, and let's verify using specific weight 0.86 times 9810 times volume, which is already computed, 81 pi over 4096. So the direct way weight is 53.43 times 9.81, and the indirect way is specific weight 0.86 times 9810 times volume of oil. So to verify, they should be equal, and the weight is 524.1 newtons. Problem 15, Part A, determine the gauge pressure at A. Fluid A is water, fluid B is air, fluid C is mercury, and fluid D is oil of specific gravity 0.94. Other given data are H1 40 cm, H sub 2 25 cm, 83, H sub 3 8 10 centimeters, H sub 4 8 centimeters, H sub 5 3 centimeters, H sub 6 60 centimeters. So part B, so that the gauge pressure at A will be 0, what would be the reading H3 in mm? Then part C, if H sub 3 stands on the right leg and not on the center leg, determine the pressure head at A in meters of oil, which is of specific gravity 0.94. The center leg, H sub 3, is now occupied with air, and the right leg for H sub 3, previously occupied with fluid D, is now occupied with fluid C. So here is the given figure. So let's mark for the solution, let's mark here as 0.1. It is exposed to the atmosphere, so its pressure is 0. Then here 0.2. Then same level, we have same fluid, homogeneous. So this is 2 prime, same pressure. Then 2 prime to this point, 3. Then this is occupied with air, so same pressure anywhere. Therefore, this is 3 prime, same pressure as that of 3. Then going directly to point A. So for part A, we sum up pressure from 1 along the legs, then down to A. So first, from 1 to 2. So take note, pressure at 1 is 0. So 0 plus 0.94 times 9.81 times 86 plus H3. H6 is 60 cm. Then H sub 3 is 10 cm. So 70 centimeters. So this total depth is 70 cm or 0.7 meter. So specific weight plus specific weight of fluid D, 0.94 times 9.81 times depth of 0.7. So that's the pressure update at level 2. Then we jump across to 2 prime, and the equation is not changed because the pressure at 2 and 2 prime are equal. The pressure at 2 and 2 prime is the same. 2 prime to 3, so that is going up, so minus specific weight of fluid C, which is mercury, 13.6 times 9.81 times H3, which is 10 cm or 0.1 meter. So minus 13.6 times 9.81 times zero point 0.1. Then 3 to 3 prime, the equation is unchanged again. Pressure is the same by principle because this is filled with gas or air. Then from 3 prime down to A, so that's plus, this is water. So 9.81 times quantity H2 plus H3 plus H4. H2 is 25 cm, H3 is 10 cm, so 35 cm. H4 is 8 cm, so 43 cm or 0.43 meter. So plus 9.81 times 0.43 meter equals pressure at A. So using your calculator there, we can now compute pressure at A, and it is equal to negative 2.668 kilopascals. So that's the answer to part A. Part B, so that the gauge pressure at A will be 0, what would be the reading H3 in mm? So we sum up pressure again from 1 to A. Then this time H3 is unknown. So beginning with P1, which is 0, we go down to 2, and take note H3 is now unknown. So 0 plus 0.94 times 9.81 times quantity H6, which is 0.6 plus H3 in meter. So that's the pressure up to 2. Then 2 to 2 prime. The equation is unchanged. 2 prime to 3. So this is mercury. So minus 13.6 times 9.81 times H3 in meter. Then 3 to 3 prime. The equation is unchanged. Then 3 prime go down to A. So plus 9.81 times H2 plus H3 plus H4. H3 is unknown. H2 is 25 cm. H4 is 8 cm, so 33 cm. So the total depth of fluid A or water is 0.33 meter, 33 cm plus H3. So plus 9.81 times quantity 0.33 plus H3 equals 0. Pressure at A is 0. That's the condition here. Divide everything by 9.81, then simplify. 0.94 times 0.6 is 0.564. 0.94 times H3 is 0.94 H3. Then minus 13.66 H3. Then plus 0.33 plus H3 equals 0 because we divide everything by 9.81. So we can now solve H3. H3 is 0.0766 meter, and it is 76.67 mm because the condition here is H3 in mm. So 76.67 mm. So that's it for part B. Then part C, this mercury here is replaced with water, and this is now mercury on the right leg. To solve for the pressure head at A in meters of oil of specific gravity 0.94. So we first solve for the pressure at A. So we will not draw another figure. We just imagine that this is now mercury fluid C. This is now air. So sum up pressure from 1 to A. So first from 1 to this level here. Take note this is now mercury. We could not proceed to 2. We just proceed to this first. So 0 plus 0.84 times 0.94 times 9.81 times 86, which is 0.6. Then take note this is now mercury. So plus 13.6 times 9.81 times 0.1 because H3 is 0.1. Then take note this is now air, and these 2 points are on the same level, and this is still mercury. So from 2 to 2 prime, jump across. So since this is now air. So from here we proceed to this point. We can mark this as 4 prime. So this is 4 prime. This is now 4 prime also because this is air. So from this point down, so take note, this is the total depth here is 43 cm or 0.43. So plus 9.81 times 0.43 equals pressure at A. So computing pressure at A is 23.09 kilopascals. So the pressure head is pressure at A divided by specific weight of fluid D, which is 0.94 times 9.81. So 23.09 divided by 0.94 times 9.81. So the pressure head at A in terms of fluid D is equal to 2.504 meter of oil of specific gravity 0.94. So that's it for this problem. Problem 16. Nitrogen gas is compressed isentropically to 60% of its volume at the temperature and pressure of 50 degrees Celsius and 300 kilopascals absolute. Determine the resulting pressure and temperature. So temperature 2 over absolute temperature 1 equals quantity Vs1 over Vs2 raised to K minus 1 equals P2 over P1 quantity raised to K minus 1 over K. So that's the formula which is derived in the lecture part. So let's use this equation to solve for resulting pressure. The isentropic exponent for diatomic gases such as nitrogen gas is 1.4. So Vs1 over 0.6 of Vs1 raised to 1.4 minus 1 equals quantity P2 over 300 raised to 1.4 minus 1 over 1.4. So cancel out Vs1 and 1 over 0.6 is 5/3 raised to 0.4 equals P2 over 300 raised to 2 over 7. So to solve for P2, 5/3 raised to 0.4. After that, raise the result to 7 halves or 3.5. Then multiply by 300, that's P sub 2. So P sub 2 is equal to 613.4 kilopascals absolute. For the temperature, take note this is absolute temperature and we express our answer resulting temperature in degrees Celsius. So we use this equation here. T sub 2 over T sub 1, where T sub 1 is 50 Celsius plus 273 kelvins now. Then Vs1 over 0.6 of Vs1 raised to 1.4 minus 1. So cancel Vs1, then we can now compute T sub 2, and it is 396.2 kelvins equals T sub 2 in degrees Celsius plus 273. So T sub 2 in degrees Celsius is 396.2 minus 273, and that's 123.2 degrees Celsius. Problem 17. What is the gas constant of oxygen in meter per Kelvin? So take note that the universal gas constant is 8,314 Newton meter moles divided by per kilogram kelvins. So MR equals 8314 Newton meter moles per kilogram kelvins. The molecular mass of oxygen gas, there are 2 atoms, so 16 times 2. So 16 times 2 is 32 moles. Oxygen is 16. Then there are 2 atoms, so 32 moles. Then the gas constant of oxygen can now be computed. 32 times gas constant of oxygen equals 8314. So the gas constant of oxygen in Newton meter per kilogram Kelvin is 259.81 Newton meter per kilogram Kelvin. So that the unit becomes meter per Kelvin, we change kilogram here to newtons so that we can cancel newtons. And 1 kilogram is 9.81 newtons. So the gas constant of oxygen is 259.81 Newton meter divided by 9.1 newtons Kelvin. So obviously the unit is now meter per Kelvin, and that is equal to 26.48 meter per Kelvin. Problem 18. Nitrogen gas is confined in a room of 30 degrees Celsius and 150 kilopascals. Determine the weight of nitrogen gas if the room measures 6 meters by 8 meters by 3 meters. So this is just an additional problem. So the weight of nitrogen gas in the confined room is specific weight of nitrogen gas times volume of the room, which is 6 by 8 by 3. So we need the specific weight, which is equal to pressure times G divided by gas constant of nitrogen times absolute temperature. So weight equals specific weight of nitrogen gas times volume. Specific weight is rho times G, or pressure over RT times G, where the density is absolute pressure divided by RT. The gas constant of nitrogen is solved first. So nitrogen gas, the molecular mass is 14 times. There are 2 atoms again. So MR equals E314, where molecular mass of nitrogen is 14 times 2. So 28 moles. Substitute here to solve for the gas constant of nitrogen. 28 times R, gas constant of nitrogen gas, is A314. So the gas constant of nitrogen gas is 296.93 Newton meter per kilogram Kelvin. Substitute here. So pressure, by the way, is 150 plus 101.3 atmospheric pressure, because this is just the gauge pressure, 150 kilopascals, so 251.3 kilopascals absolute. So substitute gamma equals 251.3 times 1000 to convert it to pascals absolute, or Newton per meter square, times 9.1 meter per second square, divided by 296.93 Newton meter per kilogram Kelvins, times temperature in Kelvins, 30 plus 273. So cancel Kelvins, cancel Newton, then this kilogram here becomes numerator. Kilogram times meter per second square is newtons. Then we have meter square meter, so meter cube. Therefore, the specific weight is obviously in newtons per cubic meter. So the specific weight of nitrogen gas is 27.4 Newton per cubic meter. Then we can now compute for the weight. 27.4 newtons per cubic meter times volume, 6 meter by 8 meters by 3 meters, so that's cubic meter. So the result is in newtons. So weight is 3946 newtons. So that's it for this entire video.